Okay, so in curve fitting, probably the easiest thing to do is, if you've got points, is to get a curve that goes through all the points. Now I want to emphasize that that's not really a good way of doing things, because in general data contains errors, and so individual data points are not right. You don't want your curve actually going through the data points. The way you want to think is that your data is correct on average. But anyway, we'll do it here. So here we have a question. Here's a point P given as coordinates, and the question is how many lines go through that point. And of course you've got infinitely many. I mean, you can talk about this line, you can talk about this line, and I will never finish writing all these lines. There's infinitely many of them. There's two, there's another one like that. However, if I specify a second point, and for technical reasons I'm not going to do it underneath or above, but over here somewhere, and it has to be a different point, yeah, Q, then there's only one line that goes through the two of them. So this would be called the interpolating line. So if you've only got two data points, and in fairness, if you've only two data points, the line of best fit is just put the line through the two of them. But I suppose one of the things I mightn't have quite said in previous lectures is that the thing about your data is there's something called the law of large numbers, and it basically says if you've got loads and loads of data, so you've got errors, so overestimates and underestimates, the more data points you have, the more likely it is that those errors are going to kind of cancel out, and that you'll have just as many positive as negative and of similar magnitudes. Okay, so that's with 2 points. This is called the interpolating polynomial. What about if we have 3 points? This is the next thing. So how about quadratics? Now, quadratics is something we're going to see again and again. Another word for them is parabolas. Now, you might just kind of know them as, you know, there's two shapes. You've got the kind of the U ones and the N ones. Now, anything that has this shape, that's not quite what makes it a parabola. There's a little bit more to it in terms of the geometry. But what you can say is that if it can be given as the y coordinate is a multiple of x squared plus a multiple of x plus a constant, where the a is non-zero, and well, that's all you certainly need, then this will be a parabola or quadratic. If the a is positive, you get this happy quadratic. If the a is negative, you get this sad quadratic. Okay, so the question here is, if you've got 2 points, say starting with P and Q, if you want to fit a quadratic, well, there's infinitely many ways. So that's a similar story to the line. When you've got a line, and you've only, when you've 1 point, there's infinitely lines that you can fit through the two of them. And similar story, when you've got 2 points, there's infinitely many parabolas. So like straight away, I could give you a sad parabola. And notice it's kind of shallow. I could do a more aggressive one that's kind of steeper. I might do something like that. I could do one like this. Now, what I'm drawing are almost certainly not parabolas, but they're just a go. But if you have a third point, say R, I'll draw it, say here, then you can show that there is only one quadratic that grows through the 3 points. So maybe something like this. Now this is going vertical, it shouldn't actually go vertical, but anyway. So 2 plus 1, 1, 2 plus 1 point defines a unique degree 2. The degree here is the highest power of x, and a polynomial just means sums of powers of x. So in other words, given 3 points, there's a unique quadratic or parabola whose graph goes through all 3 points. Okay, a bit of heavy algebra that we won't go through says if you have d plus 1 points, there's a unique polynomial of degree 2 or fewer that passes through all of these points. So for example, if you have 7 points, you can get something with x to the 6 that goes through all 7 points. So this is basically just guarantees the existence of a curve going through as many points as you want. But as we said, remember, you don't really actually want your curves to go through points, because points come from data, data comes from measurements, and measurements of errors. Now, everything we're going to do, it can be generalized for loads of points, but we're actually going to really just work with 3 points. Okay, so this is what we're going to work with. Given a set of 3 points on the plane, now they have to have a certain relationship between them. You can't have, or you see the way this goes vertical and this goes backwards. That's not a function. That's not y as a function of x. Like if I put in the x value here and getting 2 y values, that's a mistake. It shouldn't go vertical. And similarly, the points shouldn't have a vertical relationship. There should be, in other words, they should have 3 different x values. So what we're going to work with, the theorem as such is, given 3 points in the plane, there's a unique quadratic or parabola that passes through all these points. Now it actually could be a line, because if the 3 points are on a line, or line, that would be the a would be 0. Okay, so how this is going to work. So you're going to have 3 points. It's going to be like an x and a y, x and a y, x and a y. So you might present your data like this. Now we'll do examples. And you want to find the quadratic, which I'm calling L here, that at x0, the y value of the L, that's going to be called the Lagrange Interpolating quadratic, gives you exactly the corresponding y value. You put in the x1 into this formula, you end up getting the corresponding y value. And you put the final data point in, and sure enough, this Lagrange interpolating polynomial goes through the data point. And it turns out that if you can just write down a formula for this, you're done, because the theorem says there's a unique one. And this formula here works. So if we look at it, if I was to put in, say, x1 into this, so I put in x equal to x1, I'd have x1 minus x1, that's 0. That makes all of this 0. I'll get x1 minus x1, that'll make this 0, that'll all be gone. And if I put x1 into this, I get x1 minus x0, x1 minus x2, and I have x1 minus x0 divided by x1 minus x0, that gives me 1. And I have x1 minus x2 divided by x1 minus x2, that also gives me 1. So I put in x1 into this, I just get f of x1, which is exactly what it's supposed to do. You can also see here, you don't want to be dividing by 0, so none of these x values can be the same. That's basically it. I think we're going to do some examples and maybe see some pictures. So we call this the Lagrange Interpolating Polynomial degree 2. You can do this in more generality, but you actually wouldn't be. This is more just a mathematical interest. Maybe at some stage in design where you want, like say if you're designing something and you want the curve truly to go through 7 points or something like that, you could Google Lagrange polynomial calculator and it'll kind of implement this for you. But we're not, well, I don't think we're going to be examining this. No, we won't be. Okay, so we'll do some examples. Okay, so we got here. So in order to predict the number of blows required to pile depth to a certain depth, should be a space there, the following recordings were made. So the idea is here, to get to a depth of 0 was 10 blows. Now maybe somewhere on the site is kind of classed as equilibrium or whatever. And so it took 10 blows to get to that equilibrium depth. To get 1 meter down, it needed 15 more blows. Another meter down needed 40. Another meter down, it needed another 90. And then it needed whatever 135 or something like that to go down a further meter. Obviously what's happening with all the blows is the ground is getting compacted. It's making it more difficult for the pile to go deeper and deeper and deeper. Okay, so using 3 suitable data points, use Lagrange interpolation, which is just that formula on the previous page, to provide a rough estimate for the number of blows required to reach a depth of 2.5 meters. So maybe this was just an experiment done. Maybe I can't imagine actually that this would be done, because it probably costs so much to use a pile driver that you just keep banging and see how you get on. But it could be, if you wanted to predict how it was going to go, you could just find a part of the site that's typical and just start banging that. Because with that, what you'll be able to do is predict, oh, if I need to go down to 2.5 meters 40 times, you'll know how long it takes. That would be the beauty of doing something like this. Okay, so we want to find out what's going on around 2.5. Now there's there's a couple of options you could do here. You're going to use 3 points. You could use 0, 2, 4. There's some argument to use that. But I think in general for this, you want to use points that are close to 2.5. So there's going to be two options. Use either 1, 2, 3 or 2, 3, 4. And either of them, like there's no right answer here. This is like it says it. It's a rough estimate. So I don't really mind if you do 2, 3, 4 or 1, 2, 3. I'd probably be happy with 0, 2, 4. What wouldn't really make sense though would be 0, 1, 2. Because that would be extrapolating. You want to interpolate. 2, 3, 4 wouldn't be, yeah, I said 2, 3, 4 would be too bad. So let's take these points. So we're going to run with 1, 2, 3. Yeah, 2, 3, 4, there's not much between it. You could kind of calculate what's the difference going to be, but I'm quite happy with this. Okay, so this here is the, how do we know what's the x and what's the y, I suppose? Well, the y is the thing you're predicting, and the x is what you know. So the x is what we're interested in. So we're interested in what's going on at x equal to 2.5. So we're interpolating what's happening there. And that means that if the depth, now that says d, that's okay. We can just use x. This is the x, this must be the y. So we're going to have, this is x0, x1, x2, and this is f of x0, f of x1, and f of x2. Okay, so we just have to carefully use the formula on the previous page. Now, with some weird data points, the answer doesn't make sense, but we'll be certainly expecting that the 2.5 gives us something between 65 and 155. If it didn't, we've either made a mistake or this method is not appropriate, but let's go. Okay, so what we're going to say is that the number of blows, see if we can see all this, the number of blows to get to 2.5 meters, we're going to use the formula on the previous page. So that formula, now I know it because I just taught it so many years, but so you've got all the data here and the other bit is 2.5. So you just bang in to this formula here. Now I'm not going to use colors here because, yeah, it's just a question of practicing this. So it'll be 2.5 x minus, I think the first one should be x1, which is 2, x minus x2, which is 3, divided by x0 minus x1, which is 1 minus 2, times x0 minus x3, which is 1 minus 3, times the value of f at x0, which is 25. Now here I've got equals. Equals isn't really appropriate here. This is a rough estimate, so we'll use approximately equals. Okay. I continue to use the formula. Next is x minus x0, so that should be 2.5. X minus x2 divided by x1 minus x0 times x1 minus x2 times the value of the function at x1, which is 65. And I think we'll get one more. So we're going to have x minus x1, x minus x2, sorry, x minus x0, x minus x1, and then x2 minus x0, x2 minus x1, times the value of the function at x2, which is 155. Now, using a calculator, one of the things I'm not really happy to see is people putting too much into the calculator. So you really shouldn't be putting all of this in. I mean, I'll show you what I would put in. Now, I'm not sure if you'll be able to see. Well, I'll just describe it. So when I'm putting this in, I don't put 2.5 minus 2. Come on, that's just 0.5. I don't put 2.5 minus 3. That's just minus 0.5. 1 minus 2 is minus 1 by minus 2. It's minus 1 by minus 2. That's 2 by 25. Now I actually just remember what this is. It's going to be 103.75, so I won't do the rest of it. But put this as 1.5. This is minus a half. This is 1. This is minus 1. 1 by minus 1 is minus 1. This is 1.5. This is a half. This is 2. This is 1. The other thing is it's very easy with such a stupid formula to make a little mistake. How I check it is I just check these. So these numbers here must all match up, and they do. 1, 1, 2, 2. Yeah, so it's good. So this, I remember from previous years, is 103.75. Now it's a number of blows, so it's going to have to be a whole number, and so I'm going to round that to 104. Probably the other thing I should have done is said that this is essentially what we're calling L of 2.5. So that's the Lagrange interpolation of the number of blows to get to 2.5 meters. We'll see it in the picture. Note that we get a number that's between 65 and 155. If we don't get that, now you're not going to be in an exam situation, so you're going to be able to check all your answers. But if you check your answers and you can't find it, well, either you've made a mistake or the method is not appropriate. Usually I'll try and give you problems where the method is appropriate though. So you see, for this question, there's only one quadratic going through the 3 points. So this is the 125, the 265, the 3155, and we see our interpolation. So what's actually happening here, what's this formula doing? It's fitting a curve between these 3 points, because there is only one. And what we're doing is we're substituting in x equal to 2.5 into that formula, and we're getting our 104. So really, like a formula is a formula. I mean, really what I want you to understand is what the formula is doing. You're fitting a curve that goes through 3 points, and you get the equation of that curve essentially, and at the same time you're substituting in 2.5. Okay, so we'll do one more. I think there's one more on here. I do want you to understand that this is kind of a stupid way of doing things, because in general, data is wrong. Data is only correct on average. Okay, another question. So here, see how we get on. So the shear stresses of 5 specimens taken at various depths in the clay stratum is listed below. So here we're seeing, okay, as you go deeper, the stress is getting bigger. So if you want to say, if you need to know what the stress is at a certain depth, you could take 3 of these and do a Lagrange interpolation. It's just a rough estimate. It's a fair shot. Use Lagrange interpolation to estimate the shear stress at a depth of exactly 6. So we want to use points around 6. I think, so if you look at these points, they're okay, but I think it probably makes more sense to use these, because if you look at the 6, it's quite close to this. So this should be somehow in the middle if you can make it like that. So use these points, and that's what I'm going to do. Now again, we're interested in what's happening at d equal to 6. So that's like our x equal to 6. And so d is the x. And so this tau, that shouldn't be there, the stress is the y. And the y is the f of x. So this is x0, x1, x2, f of x0, f of x1, f of x2. All we have to do is use that formula again. I'll try and write it a bit better this time. So we're going to say that the shear stress at 6, which I write as tau of 6, is approximated. How are we going to approximate? So we've got these 3 data points at 4.2, 5.8, and at 8.1. We're going to find the interpolating polynomial. So that's the quadratic or the parabola, the x squared thing basically, that goes through the 3 of those, and actually using the formula at exactly the same time, we're going to substitute in x equal to 6 into that formula. So it's kind of funny, you're finding the curve and substituting in the x equal to 6 at the same time. Using the formula, like it's simple enough. You just need to practice it. You just need to do some exercises. Do it enough, you get used to you remember the formula, but that's not the point. This is really what I'm interested in. So we're putting in x equals 6, so we're talking 6x minus x1, x minus x2, so this is the formula that we're talking about, over x0 minus x1. So I was saying these second numbers are going to be the same. What goes here will be x0 and x0, so 4.2 minus 5.8, 4.2 minus 8.1 times the value of the function at 4.2, which is 19.2, plus x minus x0, x minus x2 divided by x1 minus x0 times x1 minus x2 times the value of the function x1, which is 33.5, plus, what have we got? X minus x0, x minus x1, x2 minus x0, x2 minus x1 times the value of the function there, which is 71.8. I'll have great fun here. So I'd expect my answer, because 6 is very close to 5.8, I'd expect the answer to be actually very close to 33.5. Now again, I'm gonna be careful what I put in. So this is 0.2 by minus 2.1. Is that right? Yeah. I'm a bit foggy at the maths now after, so I'll be using the calculator more than I like. So that's the first bit by 19.2. Now probably a good idea, there's probably a small lesson I can teach here. So one of the things I'm going to be going for is, it's going to be very important in this module, is rounding properly. Now what I mean by this is how many significant figures you should use. Now this is all very rough, this is very rough, so realistically you don't want to round it too much, and in fact say I'm going to go to 3 significant figures, so that's what I'm going to give the answer as, that's what I'm going to go for. Now what I'm trying to get at here is, I don't really want to put all this into the calculator. I'm very bad at pressing the wrong button, for example, or you know what I mean. So I'm going to do it one by one. Now if I'm going to 3 significant figures, I shouldn't round yet. You should only round at the end. But if you're adding things together, it's actually safe enough to round them to one more significant figure than you're going to end up with. So I'm going to round this to 4 significant figures, 4, 4, and when I add them, I'm going to get it correct to 3 significant figures. So here, I'm going to do rounding, so it's going to be approximate. So the first term here to 4 significant figures is minus 1.292. Actually, what's going to happen here is, because this is the point near 6, this is going to be the big one. And these are just going to be small corrections. Okay, next bit. So here we're getting 2.2 by minus 2.1 divided by, that looks like 1.6 by minus, well, let's just do it 5.8 minus 8.1 times 33.5. So yeah, this is going to give most of the answer. The other 2 are just going to be corrections. The 4 significant figures, 42.06. That's 4 significant figures. And then the last one, I'm getting 2.2 by 0.2 divided by, I hope there's a mistake here, 8.1 minus 4.2. I think there's a mistake. Yeah, there is. So I'm getting plus 3.522. Now, obviously, you know, you want to make slick videos. You don't want to be making mistakes on screen, but I think it actually gives a good chance to learn. Because what I'm getting at here is, it's not that, well, maybe, I mean, it's difficult. So like maybe it does grow quite a lot, but if you're looking at between 5.8 and 8, I mean, 5.8 up to 6 it's only a small bit. It's like 10%. So yeah, so from 5.8 to 6 is about 10%. So you might expect this to grow roughly about 10%. You might want to expect it to go up to, so 10% to this is about 3.3, even say 3.5. So you're expecting an answer of 37. This is way too big. So this is an example, just looking at your answer and being a little critical with it and saying, no, this can't be right. Now, the truth of the matter is, I mean, if I'm going to be honest with you, that'd be a hard thing to notice because it's not really far off. But it's a good bit off. I knew the answer down here. So what I'm going to do is, because I've written it like this, I can actually interrogate this again. What I mean by that is, I know that this is going to be the bulk of the figure, so I'm just going to calculate this again. And I can see what I've done. I've written this in as 2.2, so obviously there's a balance between what you skip on the calculator and what you not skip. So if I'm a bit more careful, 6 minus 4.2, 6 minus 8.1, 5.8 minus 4.2. Like it's very easy as well just to make a slip on the calculator, like pressing the wrong button or something like that. It's good to be able to look at your answer and say, oh, that's a bit dodgy. Yeah, and sure enough, that's what happened. So with 4 significant figures, I should have gotten 34.41. Now I'm going to add these 3 together and get an answer correct to 3 significant figures. So that minus 1.292 plus 34.41. I could include, just use the answer as the thing, but it's all rough anyway here, so it's not too big a deal. And it comes out 36.6. Now we are engineers, we should be using units, so let's do it. What is the units of stress here? Kilopascals. Okay, and so yeah, as we expected, it's close to the 33.5. Is there anything else to be said here? No, there's just going to be some exercises for you to do.